In the frigid darkness more than 15 billion miles from Earth, where sunlight is but a pale whisper and the familiar planets lie far behind, NASA's Voyager 1 spacecraft has just delivered a revelation that has stunned astrophysicists, planetary scientists, and even cosmologists. Launched in 1977 with the modest ambition of touring the outer gas giants, Voyager 1 has now far exceeded its original mission, piercing into the great black ocean of interstellar space. After nearly 5 decades in silent flight, the robotic pioneer has entered a region of space no human-built object has ever reached, and in doing so, it has made a discovery so startling, so radically at odds with our current understanding of solar boundaries, that some researchers are quietly suggesting we may need to rethink the very architecture of the solar system. What Voyager 1 has found is not simply a scientific anomaly, but a profound cosmic mystery, one that could transform our grasp of stellar environments and the invisible forces that shape them. The data trickled in slowly, just a few bits at a time, sent across the silent void via Voyager 1's ancient transmitters and received by the Deep Space Network on Earth. These readings, beamed over the course of several painstaking months, painted a picture both beautiful and bewildering. Voyager's onboard instruments, particularly its plasma wave subsystem and long-serving magnetometer, began detecting subtle but consistent deviations in the expected magnetic environment beyond the heliopause, the boundary where the solar wind meets the interstellar medium. For decades, scientists believed this region to be chaotic and turbulent, a kind of cosmic wash where solar particles are decelerated, scattered, and eventually merged with the interstellar flow. But the data from Voyager 1 told a different story. It showed not the expected turbulence, but something astonishing, a highly ordered, coherent magnetic field that rippled in what appeared to be regular intervals, forming what one researcher called a living membrane of magnetism. Initially, skepticism dominated. Voyager 1 is an aging machine, running on fading reserves of power generated by its radioactive thermoelectric generator. Could its instruments be failing? Could the data be corrupted by noise or decay? Teams of engineers and scientists launched exhaustive diagnostics, cross-referencing readings from Voyager 2, which is on a similar path, though trailing by tens of millions of miles. The verdict came back: the readings were valid. This was not sensor error or instrumentation fatigue. This was something real, an entirely new and unexpected magnetic structure forming at the edge of the Sun's influence. And unlike anything in prior heliospheric models, it was not a jumbled mess of interactions, but a finely tuned, seemingly deliberate configuration, suggesting a level of order no one had thought possible in such a hostile, high-energy environment. More detailed analysis revealed that this magnetic structure displayed oscillations that were both large in scale and unusual in frequency. They didn't match any known periodic behavior of solar wind interactions, interstellar shocks, or even cosmic ray interference. Instead, they formed a kind of quasi-crystalline lattice, an arrangement where the magnetic field lines aligned themselves in spatially repetitive patterns. To put it another way, the outer edge of our solar system, long assumed to be a roiling cauldron of unpredictability, looked more like a massive, geometric force field. This was a revelation that sent shockwaves through the astrophysical community. Such precise arrangements aren't supposed to happen at these scales, certainly not in magnetized plasma zones, which are typically dominated by turbulence, reconnection, and entropy. This startling realization opened the door to a wave of theoretical speculation. If this structured field was real, and all signs now pointed to it being so, then what force could be responsible for its formation? Theories began flying from every corner of the physics community. One hypothesis explored the possibility that dark matter, mysterious, unseen mass believed to make up most of the matter in the universe, might exert influence at the boundary, shaping the heliopause through gravitational filaments or magnetic interaction. However, this would require dark matter to have far more interactive properties than currently theorized. Another camp floated the idea of magnetic resonance between our Sun and an unknown interstellar field, an overlapping of electromagnetic forces that, under the right conditions, might give rise to standing waves or interference patterns. If true, it would suggest the heliosphere is not a simple shell, but a dynamic participant in a vast, galaxy-wide electromagnetic network. Whatever the underlying cause, Voyager 1's discovery had unveiled something that fundamentally altered our view of the solar system's outer limits. The heliopause was no longer just a transitional zone, it was now suspected to be a kind of semi-permeable skin, an interface with complex structural properties. This meant the solar system didn't end in a gradual diffusion of particles and magnetic chaos. It ended in form, in shape, in structure. Some scientists began likening it to the skin of a living organism, a functional layer that filtered, reacted, and communicated with its environment. The implication stretched far and wide. Perhaps all stars are encased in such membranes. Perhaps this is a universal feature of stellar systems, one we've only just begun to understand. Such a model changes everything. Our current understanding of stellar boundaries, how stars influence their surroundings, how galactic matter flows, how particles travel across interstellar space, may need dramatic revision. If magnetic membranes are a widespread phenomenon, they could serve as regulators for cosmic ray flow, determining which particles make it into a system and which are kept out. This has immediate consequences for planetary atmospheres and even biology. High-energy particles have been linked to mutation rates, cloud formation, and even long-term climate trends. Could the heliopause be a kind of galactic immune system, shaping the internal environments of star systems in subtle but critical ways? There is, of course, a more provocative question lurking beneath the surface, one that many scientists hesitate to ask aloud. What if this structure isn't entirely natural? What if the precision of the magnetic lattice, the regularity, the rhythm, the unexpected energy behavior, was not the product of random plasma dynamics, but intentional design? Some fringe theorists have long proposed that advanced civilizations might manipulate field structures on a grand scale, not with matter and machines, but through the modulation of gravity and magnetism. Such structures, they argue, would be effectively invisible, undetectable except by probes like Voyager stumbling upon them. While most scientists scoff at the idea, a few now admit that Voyager's findings have introduced a level of ordered complexity that is difficult to reconcile with natural processes alone. Supporting this more radical view is the peculiar behavior of cosmic rays near the boundary. As Voyager 1 crossed the structured region, it observed sharp, non-random discontinuities in particle flow. High-energy particles that should have passed through were deflected. Others were allowed to enter. The data suggested not chaotic filtering, but pattern-based selection, almost as if the magnetic membrane were acting as a sieve, sorting particles by unknown criteria. This is unlike anything seen in conventional astrophysical models. If confirmed, it would mean the heliopause is more than just a magnetic interface. It could be a gatekeeper of sorts, managing energy and matter exchange in a way that feels eerily deliberate. Adding to the intrigue are the low-frequency radio emissions that Voyager 1 recorded in tandem with its magnetic observations. These were not the random bursts of background noise expected in deep space. They were structured, modulated. Their timing was tight. Their frequencies hinted at resonance phenomena not seen before at this scale. Initially assumed to be the aftershock of solar events, further analysis showed no correlation with solar flare activity or coronal mass ejections. Instead, these signals peaked precisely when Voyager passed through the most structured sections of the magnetic lattice, leading some to speculate that the field itself might be emitting radio frequency energy, either as a side effect of plasma interaction or, more tantalizingly, as a form of low-band communication. The ramifications of this extend into mission planning for future space exploration. We now face the prospect that the boundary of the solar system is not a barrier to be broken, but a complex environment to be studied. Spacecraft engineers are already rethinking how we might design new probes to map these structures in detail. Instead of simply pushing beyond the heliopause, what if we could linger at its edge? Imagine probes that could surf the magnetic waves, writing and analyzing the field like satellites do Earth's ionosphere. This could provide insights not just into our Sun, but into how stellar environments interact across galactic scales. Moreover, this discovery could inform the search for extraterrestrial life. If magnetic structures regulate what enters and exits a solar system, then they may play a critical role in determining whether life-sustaining materials reach the planets inside. The transport of organic molecules, charged dust particles, even frozen water fragments, could be influenced by the heliopause filtering mechanism. Life, in this view, is not merely the result of planetary conditions, but of galactic positioning and stellar shielding. In other words, the heliopause might be the solar system's first and most important defense, and gatekeeper, for life itself. Philosophically, Voyager's discovery resonates on an even deeper level. We have long viewed our place in the cosmos as a tiny bastion of order in a sea of chaos. But what if that boundary is not as sharp as we believed? What if order exists in the spaces between stars? What if, far from being a silent void, the interstellar medium is alive with structure, with rhythm, with purpose? Voyager 1, that tiny, persistent emissary of human curiosity, has pierced the veil and found not the expected randomness, but a kind of cosmic intention, whether natural or otherwise. No, this does not confirm alien intelligence, nor does it rewrite the laws of physics overnight. But it does whisper of something deeper, something humbling. It reminds us that the universe, no matter how much we study it, always holds one more mystery behind the curtain. Voyager 1 has traveled farther than any object in human history. In its final years, it has not just broken records, it has broken paradigms. The edge, we thought, was the end. But now, it looks increasingly like a beginning.